So here's our chapter, thermochemistry. Like I said, this is all about energy. Stoichiometric calculations involving energy. So we'll see an enthalpy term listed next to the reaction, and that's going to be the energy associated with that reaction, whether the reaction is giving off or absorbing energy. That sign will tell you that, and the energy value is the same as everything else in the equation. It depends on the coefficients. Okay, so the energy is going to be associated with however that reaction is balanced. If I multiply that reaction by 2, well, then the energy is going to be twice as much, right? You should realize that, right? Just no different than baking something like that. Double the recipe, you get twice as much. You get twice as much energy also from a chemical reaction. Make sure you know heat capacity is, and specific heat capacity specifically. We don't use heat capacity that much. We use specific heat capacity and specific and molar heat capacity. And calculations related to those. There's a lot of calculations in this chapter, a lot of calorimetry. Calorimetry is the means in which we use to measure these. I mentioned that in the when talking about the outline the other day. If you take physical chemistry, you'll actually do some calorimetric experiments and measure enthalpies and things like that. We use Hess's law to be able to manipulate our way to finding an enthalpy of a reaction when we don't know it, but we might know some other reactions. And we could take those like puzzle pieces and kind of manipulate them to get to an enthalpy value you might be interested in. I think I did something in the videos kind of showing you that. And then formation reactions, that's just us standardizing and standardizing and tabulating things like we do in all sciences, engineering, things like this, not just those fields, economics, whatever. We like to have tables where we can look at numbers and compare things. So that's what formations are going to be. All right. So you had your quiz this morning. Any questions on what a state function is? Will someone share with me what a state function is if no one has a question? How'd it go? Very good. A function whose result is not impacted by the pathway, not dependent on the pathway, right? I think in the video, maybe I give an example of altitude change. It would be considered a state function. Doesn't matter what direction you go, how you get there. The altitude difference between here and, I think I said Klingman's dome is the same regardless of how you get there, but distance is not a state function, right? That's going to depend on the path you take. Endothermic, exothermic, what are the signs of those? Plus and minus, plus for endothermic, negative for exothermic, right? And of course, we're going to use heat, Q for heat throughout the chapter, and enthalpy will be H. And we're usually looking at the change in heat enthalpy when we talk about a reaction. And what is enthalpy? What's enthalpy? Yes. Very good. Heat energy at constant pressure. That's all it is. So, okay. Units will kind of hit throughout the chapter, but enthalpy is just a simplified way of looking at our system when we don't have to worry about work and that pressure is constant. We can just use that. And that's going to be very common for a lot of reactions. I think I mentioned that the other day when we had our outline out. So, first law of thermodynamics. I think I put a question on the quiz about that, so it should have been pretty easy, or maybe, I think it was. Didn't I put something on there? States that energy cannot be created or destroyed. You've known this for a long time. I think I put something on there about chicken soup. Hopefully, if I did it, was that on there? You didn't choose that one? What's that? Did it? I can't remember half the stuff I do. I think it was Lincoln, actually. Was it really? All right. Total energy of the universe is constant. So this is something we know for a long time, and you've actually probably been exposed to this way back as far as early high school, maybe even middle school. Energy is neither created nor destroyed. So the idea is the energy can change forms, it can be released and absorbed, take on different forms, right? But the energy of the universe is constant. And the universe is made up of that system and the surroundings. And you can define the system however you like, but it's important you define the system because that's going to allow you to measure what's happening. Okay, if you want to know what's happening with the system, it has to be defined, right? Can't measure it if you don't know what that definition is. And in some cases, the system could be just the species that are doing the reacting, or it could be the species in the solvent, or it could be the whole chamber where the action is taking place, like a calorimeter. That would be our system. Everything outside the calorimeter would maybe the surroundings, depending on how you define it. So your book spends a lot of time in the early pages talking about, energy of the system, and work and all of this. And we're not going to spend much time on that. I mentioned that to you already as you read this, to not, just read through it. Don't worry about, mastering it or anything like that. We're going to pretty much do away with work. We're not going to deal with it. It's too advanced for Gen Chem. And that just means that, something besides energy is being released and absorbed by the system. There's being work done on the system, or the system's doing work. The example I gave you was like gases. The easiest way to visualize it is gases driving a piston, right? That would be the system doing work on the surroundings. So here's 3 systems here, and that middle one, it's not very clear. It's supposed to have a lid on it, but it says closed system, cup of soup with a lid, but you can't really see the lids. I'm going to add my own lid. Okay. Now, energy can still get out because that lid is not going to be. The idea here is this is a thermos, super insulated, right? Now, there's no such thing as a truly contained system where no energy is lost. We know that thermos is going to lose heat over time. Of course, in the lab, we can make something a little bit better, but we always are going to lose heat. Okay, we can't stop that from happening. We can just make super, insulated systems, but we could say that's an isolated system, at least for a period of time that we might study it, that very little energy is going to escape. Supposed in the middle one, it's letting out a lot of energy, but there's no input or output of any sort of matter other than the energy that we're talking about. So no matter input or output. And then the last one, it's completely open system. So you can have stuff being put in and stuff being lost. And you can lose water vapor, right? That's the key one there that you can think about instead of, the silly stuff like grated cheese and stuff like that. You can think about a hot system losing water vapor. That's not just heat. That's actually losing molecules of water. So that's an open system. And for us, to be honest with you, we're not going to deal that much with systems that are losing stuff. We're going to think of our systems as being pretty much like the middle one, where we're just going to be dealing with the exchange of heat between the surroundings and our system. Okay. So here we go with the conventions. We said the signs. We've already said this. Megan said that exothermic and endothermic. Endothermic's positive. Exothermic is negative. And Q, we said, is going to be our symbol for heat. Okay. And so if I have like water in a tub and I heat it, is that an endothermic or exothermic system relative to the water? Endothermic, right? It's going to absorb the heat and it's going to evaporate, and the water molecules will have taken that heat and converted it into water vapor. When you sweat, of course, the whole purpose of sweating is to cool you down, right? The evaporation of the water takes the heat with it, and that has a cooling effect on you. It's the whole purpose of sweating. All right, enthalpy and enthalpy changes. So we could treat Q and H basically the same as far as how we treat them. One is constant pressure, one is not, but the terms and how we calculate and all that are pretty much the same. And basically enthalpy, as we said, one of our students said to us that it's just heat at constant pressure. So we can look at changes by just adding a delta symbol, and that's always what we're going to do, because think about it, I can't possibly quantify the energy associated with a chemical system. It's impossible. Think about all the energies associated. I mean, literally, you have energy in the nucleus, right? You get the electrons, right? You got energy in the bonds. That's the the energy on a micro scale, and then there's the macro scale energy, the molecules vibrating, any heat coming in and out. We can't quantify that. It's impossible. So we never try to quantify total energy of a system. We simply look at changes in the energy. Here's my system at point A. I can measure how much energy changes. And for us, it's easy to do in terms of chemical reactions. Just look at heat, right? Heat given off. I can measure heat easily with temperature. So if I see that my chemical reaction is going on and my thermometer is going up, I know energy is being given off and I can measure it. Okay? That's the easiest way to do it, is look at those changes. We don't have to worry about exactly what's happening in all the molecules and in the system before and afterwards. We're simply going to look at the change, and we can do that by measuring temperature. Okay? Questions? All right, so phase change, enthalpies. Some phase changes require energy to be added to the system. So enthalpy of fusion, which is the term we use for melting solid to a liquid at the freezing point. Freezing point, melting point are the same thing. It just depends on what direction you're thinking about it, right? Freezing point, melting point, the exact same thing. Okay. If you're thinking about from the liquid's perspective, it's the freezing point. If you're thinking about from the solid's perspective, it's the melting point. And then enthalpy of vaporization, that would be converting it to a vapor, obviously. And they're usually reported as per amount of substance, because it's just straight heat capacity. Maybe I got rid of that. Oh, here we go. No, never mind. It's coming up. Right. All right. So, and you can see different values here. We have methane, which you're familiar with, water, ammonia, ethanol, some common ones. And you see it in grams per mole. I'm sorry, that's the molar mass. And then you see in kilojoules per mole. And for both of them, then you have the heat of fusion and the heat of vaporization. So you can barely see that. Middle column is fusion, and on the right is vaporization. And you scroll down and you notice that for water, we give it at multiple temperatures. I'm sorry. Yes, at multiple temperatures. And that's because it varies. So you can change the pressure, and the boiling point changes when you change the pressure. So if I'm sitting up at some peak, right? 10,000 feet up in the air, and I'm boiling water. The boiling point, it actually takes you longer to like hard boil an egg at a high altitude, because the boiling point is low, right? So when you think about boiling point, we'll get into this in Gen Chem 2. We're not going to talk about vapor pressure here. It's too soon. But think about it as, you know, the air, column of air sitting on the water, pushing on it. So when you're higher up, less of a column on that water, so it's easier for the water to escape. One way of thinking about it, it's not exactly right. We'll talk about equilibrium vapor pressure in Gen Chem 2. But the boiling point is lower at a higher altitude. So if my water is boiling at 90 degrees C instead of 100 degrees C, it takes longer to cook something, right? So pressure affects the boiling point. Okay, so that's why we have all these different heats of vaporization, vaporization values, because the same way pressure affects boiling point, it affects escaping of the liquid into a vapor. It's pretty much the same thing. You can have vaporization not at the boiling point, right? A liquid could be sitting there, right? You leave a glass of water here and come back in a few years, it's completely evaporated, right? Gone. So this is dependent on pressure, and that's why these don't change that much with pressure. So that's why you don't see multiple values. The changes are only when you get to extremes. But here it's significant enough. They're giving you different heats of vaporization at different temperatures. And the only way to see that change, I mean, the only way to, I'm butchering this, sorry, but the only way to, institute that is through a pressure change, basically. All right. Otherwise, you can see that water's heat of vaporization and its heat of fusion are higher than anything else on the list. Okay, and in some cases significantly higher than some. And you might guess, and we'll cover this in Gen Chem 2, methane, CH4, smallest hydrocarbon, it's what you use to heat your house, right? If you've got gas heat, it's a gas at room temperature, right? So you would expect it to have a pretty low heat of vaporization, right? Because it's a gas at room temperature, right? So that means that there's enough energy in this room. If I were to take, liquid methane and open it up in here, it instantly turn into a gas, right? Because there's enough energy in this room to break apart those bonds. So that's what makes something exist as a gas, a liquid, or solid at a given temperature. We'll cover that a lot in Gen Chem 2. So here's our heating curve. We've been talking about melting stuff and boiling stuff. In this case, we have ice at minus 18 degrees. See, you can do science at home. You don't have to do it only. And look how happy she is. So if you do stuff like this at home, you'll be happy too. All right. So you've got this ice at minus 18 degrees C. We're right here. We're going to heat it up. And once we reach that melting point, I mentioned this the other day during the outline, then all the energy that goes into it no longer changes the temperature. So this is the temperature change on the y-axis, and it's not changing. So all the energy is going into converting the ice that is now at 0 degrees C into water at 0 degrees C. Then when all of it's water, the energy now goes into vibrating all those water molecules, right? And the temperature increases until you get to the boiling point. And these lines are different sizes, not accidentally. What does that mean to you? Someone explain to me what that means in terms of water, why they're both phase changes, but why is this one so much bigger than this one?
It takes more energy to change it to a vapor than to a liquid.
Very good. It takes much more energy to convert water from a liquid to a vapor than it does to convert ice to a liquid. And think about it, what you're doing effectively is going from a solid to a liquid. You still got bonding going on, right? Between the water molecules. Here's where you're completely separating them out. So it takes a lot more energy. Here you're kind of just, breaking the matrix down, but you still have all the hydrogen bonding that holds the water molecules in a liquid. Otherwise, it would be a gas. The bonds between molecules are really weak. That's what makes something a gas at room temperature, right? CO2 has very weak bonds between the individual CO2 molecules. So I've got to lower the temperature really low to get liquid CO2 and even lower to get solid CO2, which is a dry ice, right? Dry ice, you can actually see it sublimating, right? It goes straight from solid to gas because the bonding is so weak. It just boom goes right off into the gas phase, and you get that nice smoke effect. If you've ever dropped dry ice in water, it's so cool. All right, so those are your phase changes. Questions on phase changes. It doesn't matter what the substance is. You're going to have regions in which the temperature doesn't change, but the size, obviously, your boiling points and melting points will all be different, and the sizes of these lines will be different depending on the substance. But the same general trend will hold. So now we're going to kind of relate temperature change and heat flow. So there's our heat Q. And we've got this heat capacity, CP. And we'll introduce it, but then we'll say, useless. We're not going to bother it because it's not defined per amount of substance. If I tell you the heat capacity of an object is, 25 joules. Well, it's like, well, 25 joules, per what? Per gram, per mole, what? For the whole object, who cares, right? You want to know, that's how you standardize things, right? You do it per mole or per gram, so you can compare them. Now, if I've got a big chunk of iron and a small little pebble of gold, then I tell you the two heat capacities, well, who cares? What is it per gram or per mole? So heat capacity is not per amount of substance, so it's not particularly useful. Just the energy required to raise the temperature of an object by 1 degree C at constant pressure. Now, it might be used a little bit more in engineering if you're talking about like a particular part in a car and they want to know how much the temperature changes. They don't care per gram. They want to know, hey, this piston, how much does this temperature change per, some sort of heat resistant material type thing, where you're thinking about like an object more than, a reacting species, where it might be important in engineering for a particular object. Designing something for a space shuttle, like a shield, the heat shield they put on, the different panels, they might want to know, hey, what's the heat capacity of this panel? But in other words, for us, we're going to be doing more specific, where we're doing either per gram or per mole. Okay. So you look at these equations, and once again, we won't use this, but these two are pretty much the same, right? You got your change in temperature. So what this means is that if you want to define it, Cp is equal to Q over N delta T. So the specific heat of a substance is the energy change, the Q, per mole temperature, in a sense. That's kind of what you want to quantify for a substance is, okay, what's the specific heat capacity of a substance? Well, I want to know per how much material, right? And I want to know for each temperature increment. That makes sense. That's the easy way to compare things. That's one way to look at this equation too. Another way to look at it is just like this. The heat that's needed to raise the temperature is going to depend on the mass of the material and the type of material. The CS is the heat capacity that is unique to that substance. So iron has a heat capacity. Water has a heat capacity. Obviously, you want to know how much heat you need, you have to know what the specific substance is. If you want to know, hey, how much heat it's going to take it to change this block of iron from 5 degrees C to 10 degrees C. I have to heat this block of iron up 5 degrees C to 10 degrees C. How much heat is it going to take? Well, I need to know the mass of the block. I need to know the specific heat capacity of the material. And I've given you the temperature change. That's where we're going to use this. All right. Again, if you look at water at 25 degrees C, you can see it's got different heat capacities depending on temperature. We'll pretty much just use 25 degrees C. If you're ever given a problem, they don't give you the temperature. That you just assume that. But see, it's pretty high again, right? Look at this one in terms of per gram. Look at the metals, right? Really low. And it makes sense, right? We make our pans out of metals. We want them to heat up quick. They have low heat capacity. Water is a high heat capacity. What's that mean? What does that mean to you in a qualitative sense? It means the higher the heat capacity, the more energy it takes to raise its temperature. So if you want a good insulator, right, it's got to have a high heat capacity. You don't want something that want it to insulate. You don't want to change temperature readily, right? Air is pretty low compared to water, but still much better than all your metals, right? It's the idea of having like storm windows and having a gap in between. The air acts as an insulator. Now people don't use storm windows as much because they just use just better glass windows and double pane windows. Old houses I grew up in, those had storm windows. All right. So this is just molar and per gram. And just use the one that you need based on your units. Always look at your units, make sure you're using the right one. Look up the right one, whether you did smart work in an exam or whatever. So here's turning snow into boiling water. So now what we have to realize is there's I do that first. There it is. But I don't have a slide. Let's see. So we do it here. So if you're doing a phase change, then the equation has to change, right? Because there's no temperature change during a phase change. So the equations basically just become Q, amount of material. That's the way I used to think about it. Your Q's are always going to be amount of material times whatever you're doing. If you're raising the heat of a piece of metal, you need specific heat of the metal. If you're melting something, you need a heat of fusion. And then if it's not a phase change, you need a delta T. If it is a phase change, it just becomes Q equals right here. For melting something, no delta T, right? It's just the amount of material times the heat of fusion. So you see what we're doing now? We've got three-step equation. We're going to calculate the energy associated with taking snow that's at minus 18 degrees C and heating it all the way up to water at 100 degrees C. So effectively, what you're doing is this first step here, right? Heating it using this equation. Your delta T is 18, right? Change in temperature. The mass of water, whatever mass, we got 275 grams. And then you use your 4.18, your CS, joules per gram degree C. There it is. That's that first equation right there will be Q is equal to 275 grams times 4.18 grams per degree. What is it per degree C? I'm sorry, joule. I forgot joules. Joules per gram degree C. And you can just fact check that with, looking at your equation. Joules per gram degree C times my change in temperature was 18 degrees C. And that's going to be the Q for that first step. All right. Then you can do that equation again, only this equation minus the delta T and with the heat of fusion, right? Add it to the first one. And then you do it a third time. And this time you're back to the same equation. Only difference is the mass is the same. And your C now is, okay, I'm sorry, that's solid. We have solid water. So the first time we would use this. That's the closest one, 211. So it's water at minus 10 degrees C. We're minus 18. We don't have a value for minus 18. So we would use the 211 there, not the use that. Oops. And then you would use this equation again, a third. So the second equation is Q is equal to, and moles, you have to convert it to moles. So it's the 275 divided by 18, right? Grams per mole. And then the heat of fusion of water, which is back here. And we got it in moles, 6.01. So we can 6.01. Per mole. That's the second step. Then the third step will be Q is equal to, back to that first equation again, kind of 275 grams. Now we use the 4.18. And then we're heating it up 100 degrees, right? And you can add all three of those together, and that will be the heat necessary to take water from minus 18 up to water at 100. I'm sorry, ice at minus 18 up to water at 100 degrees. You can just add all three together. That's too long for an individual question on exam, but treat them as individual problems. You look like you're really staring at that. So what? Something not make sense?
I just can't.
Yeah, neither can I. So don't worry. So yeah, the 275 grams, right? Yeah, so this here is just converting to moles. because this is in moles here. So it's 18 grams per mole. That's all that is. It's converting it to moles. So keep an eye on your units. Also realize, let me double check. That might be kilojoules. Yes. So that's kilojoules. That's the other one you got to worry about. So this is actually kilojoules here. Okay. So when you add them, right? This one's in kilojoules. These two are all in joules. We'll do a simpler one. This one's involved. So if you look at your book, there's two really involved ones. They're good, like I said, to treat them as individual problems. The whole thing is too much for a single question on exam. But 10.4 is, here it is here. It's a phase change type of question. They ask you some qualitative stuff, but then they ask you here, we're cooling the water, freezing the water. In this case, we're going the opposite direction, cooling the ice. 3 steps. Similar to what we just did, moving the opposite direction. Do these because they're great as individual questions, and you learn how to use these different equations, right? And then there's 10.5, and I'll do one. I forget what my example is, but and here's 10.5, which is, this is really difficult because you're calculating the temperature. Okay, that's the only difference, is now you got to calculate the final temperature. That's what they're asking you. Okay, so exercise your brain. You're not going to see something like this on my exam, but I always tell students, your brain's like anything. You know, if you're training, you're a golfer. If you're training to do something, a marathon, you don't just run, right? You do different exercises to strengthen different parts of your body, different things, mental and physical exercises to prepare, right? You don't just do one type of training. It's the same thing with your brain. Just because you might not see a question like this on the exam, still challenge yourself to do it. And at least look at it and see if you can understand what they did, okay? All right, let's see which one I have. I have how much energy is needed to melt 50 grams of ice that is initially at minus 18 degrees C. So similar to what we just did, only we're not going to take it all the way up to 100 degrees C. It's only 2 steps in this case. This is much more reasonable for an exam question. Oh, I guess I need to switch back. But the same approach. So 50 grams of ice at minus 18 degrees C. So the first thing we need to do is take the 50 grams of ice at minus 18 degrees C and heat it up to 0 degrees C, right? And then we need to melt it to get the water. And that water is still at 0 degrees C, so we don't have to do anything else. So you can see we've only got 2 calculations to do, 2 Q's, if you will, instead of 3. So the first one is not a phase change, so it's going to be a Q amount of material, right? Delta T. I just use C for all these things. I don't use subscripts. I just use C as a placeholder in my head. And they have CS, I think, for specific heat capacity. Okay, that's the first step. Now we've got the mass, 50 grams. And we'll go get our heat of specific heat of ice. Let's look up our C for ice. There it is there. We'll use that 211 again because we have minus 10. That's better than 25, obviously. So 2.11 joules per gram degree C. And then our change in temperature, we're going from 18. I don't do some, and I'll show you this later. Delta T is T final minus T initial. I always just look at the difference. I don't worry about negative signs. And I'll show you that later why. But delta T is 18 degrees C. That's all we care about, right? Change in temperature. You don't have to worry about signs here anyway. But later on, there is a case where we have to worry about signs. So I need someone to do that calculation for me. That's the amount of energy needed, heat, to take ice at minus 18 and get it to ice at the melting point, 0 degrees C. Anybody else? And that's going to be joules, because degrees C is history and grams is history. And that's what we want. We're calculating Q, which is energy, we want joules. So units are things like joules, kilojoules. We introduce calories in this chapter. We do that somewhere. Maybe it's Gen Chem 2. Calories are units of heat, energy also. Okay, now we need to do it for, what do we've got? We've got Q is equal to, and the only equation then is N. These are all based on N. So we need the heat of fusion of water. Heat of fusion is the 6.01 kilojoules per mole. And you see we need moles. So we've got 50 grams times 18 grams per mole, right? Whoops. That'll give me my moles, and then it was a 6 point, what was it, 6.01? So grams are history, moles are history, we'll get kilojoules for that. It'd be about, well, we just do it in our head, it's 300. We can ignore the 0.01. Right? Oh, I forgot to divide by 18, so we can't do that. So someone's got to do it on the calculator for me. Thank you. I missed the. What'd you get? 16.69. Someone can confirm that? Okay. Whoops. And remember, that's kilojoules. So we can just convert this top one to kilojoules. And then it becomes 16.69 plus 1.899. So we got about 18.6 kilojoules, right? For our answer. So that's the energy necessary to heat ice at minus 18 degrees C to water at 0 degrees C. Questions?
On the phase changes for the fusions that you use the value that it's going to or coming from?
There's only one value. So heat of fusion will be whether or not you're melting the ice or freezing the water. Heat of vaporization will be either whether you're boiling it or condensing it, doesn't matter.
So like in this example, if you're going from the solid to the liquid, you use the liquid, like the 6.01.
This is the same regardless. That's what I'm saying.
Okay.
That's the heat of fusion, or if you will, it's called the heat of fusion. You would use it whether or not you're melting something or you're freezing something.
Okay.
just that the energy would be moving in the opposite direction. You'd be taking the energy out if you're freezing it, as opposed to putting it in. But the number's the same. Yeah, there's only one value. So, we call it heat of fusion, but it's for melting or freezing you use it. That makes sense? Anything else?
Does it matter if it's in kilojoules or joules? 'Cause
No,
I didn't mind joules.
Yeah, they're both acceptable heat answers, just if you're doing a multiple choice exam, obviously. Other question. All right. So we can use these calorimeters. In this case, we can use, this is the part where I'm talking about this negative sign. So the specific heat of a metal, to figure it out. It's a common way. I don't know what you guys are doing in lab anymore, but we should do something similar to this. Did you guys do anything like this? Or are you doing something this week, maybe?
Coffee cup.
Yeah. Is it with piece of metal, or is it just like a reaction? It's what? Yeah, but are you using a hunk of metal in there, or is it just like a reaction to solutions?
Powdered metal.
Powdered metal? Oh, okay. Oh, like magnesium maybe? Or something?
Yeah, magnesium.
Okay. So, what you can do is often that's good. That's a chemical reaction one though. So what you can do is you can take a hunk of metal and you can actually figure out what its heat capacity is by this idea right here. So let's say I take a metal, right? A block of metal, and I heat it up to 80 degrees C. And then I drop it in water. The heat lost by the metal is gained by the water. Assuming no heat is lost at the top of your cup or whatever, right? That's what you always have to do in lab, and assume there's no heat loss. That's where your error comes from, of course. There is heat loss. But any heat lost by that metal is gained by the water. And if I know how much water is in there, and I know the heat capacity of water, right? I know how much water is in there, so I know the mass. I know the heat capacity of water. I can measure the temperature change of the water. Then I can figure out Q for the water, right? Is everybody following me? Yes? Okay. So if I know what the Q for the water is, this is where I don't bother using the negative sign. I simply solve this equation twice. I solve it for water, right? And I get the Q because I know the mass of water. I set up my own calorimeter. I know the specific heat of water. I'm going to measure the temperature change with the thermometer. I'm going to calculate Q. Then I'm going to take that Q value and put it in for the metal. And I'm going to have a Q. I know the mass of my metal. I can weigh it. I know the temperature change for the metals. The metal's going to start at 80 degrees C. I think I asked a question like this on the quiz. The final temperature will be the same of the metal and the water. Once they come to that thermal equilibrium, right? The water will rise in temperature. The metal will drop until they're the same temperature, right? Yeah. So the final temperature is the same. So the metal might drop from, say, 80 degrees C down to 30 degrees C, and the water goes from 25 to up to 30, whatever. So now I've got the temperature change. I've got the M for the metal. I got this from the first calculation. I can now calculate my specific heat for the metal. You see? Because the heat lost by the metal is gained by the water. So that's why they have the negative sign. What they want you to do is kind of like set them equal to each other, right? And realize the final temperature of the metal is lower than the initial temperature. So T final minus T initial for the metal will be negative. That's where the negative sign comes from. You see? All I do is just solve it twice. I don't worry about the negative sign. I simply solve it for Q for the water, put the Q in, and then solve it for this for the metal. I don't worry about setting them equal to each other, worrying about the negative sign, worry about the T final, T initial. I just go, what's the temperature change? As a positive number, what's the temperature change? Solve the equation twice. It's no different, really. It's just whether you want to set them equal to each other with a negative sign there. So effectively, you would do it like this, Q, M, C, whoops, not Q, sorry. You would have it like this if you like to do it, if you want to do it like this. MC delta T equals negative MC delta T. And this one is for the water. And this one is for the metal. And you put in your T final for the metal being less, right? That's going to get rid of the negative sign. You're going to solve it like that. It's just not the way I choose to do it. Questions? So we can use this idea, this calorimetry, like you did in lab, and we can calculate things like specific heat capacity of the metal. We can calculate energy changes for reactions, right? If we've got a nice insulated calorimeter system, we can just figure out the heat associated with a chemical reaction. So this is just a device we're going to use. This is how we get these tabulated data, basically, is using these calorimeters. The magnitude of energy absorbed or released during a chemical reaction is proportional to the quantity of the reactants. I mentioned this at the very beginning of today's lecture. If I have a reaction A plus B going to C, and I have an enthalpy value equal to 20 kilojoules, and then I take that reaction and multiply it by 2, and I wind up with 2A, 2B, 2C. Well, you better multiply this by 2 also, because the heat's going to be double. That shouldn't be surprising to you at all. So it really depends on the difference in the enthalpy between its reactants and products. So effectively, when you think about reactants going to products, if energy is being released, that means the reactants are up here. If this is my energy profile, and this is just time or the reaction progress, and the products are down here, that means the products have lower energy than the reactants, right? So if they have lower energy, what do you think that means in terms of stability? Less stable? More stable. Yes, more stable. She can tell the opposite, by the way. Responding to her answer. Giving off energy, right? What are we talking about? Getting to a lower state of energy, being more stable. Too much energy, you're unstable, right? Lower energy, you're relaxed. More grounded. All right, so I think did I ask that on the quiz? I know I was thinking about it. Combustion one, I said, or something. Was it combustion or was it just a reaction in general? I think I said that.
Yeah, just a combustion reaction.
Okay, right. So combustion reactions are very favorable. We get them started, they go, which means the CO2 in the water are more stable because they're products than the reacting species, because it happens kind of, and we'll talk about this in Gen Chem 2, spontaneously. So looking at whether the energy is given off or absorbed tells you something about the stability of the reactants in the products. So here are some thermochemical equations. And the energy associated with this one is here. And the energy associated with this one is here. And you can see that it's basically 1/2 of the previous reaction, right? And then the enthalpy is 1/2 of it. That's all. That's all this is showing, is that this reaction has twice as much material, 2, 13, 8, and 10, versus 1, 13/2, 4, and 5, and then the enthalpy value is 1/2. So if we're going to use a calorimeter, we kind of have to take this approach with this Q. So just our MC delta T again. This is kind of the same equation, just used in different approaches, that's all. So here we have, this is straight from the book, 0.2 liters of 0.2 molar HCl. You've got a volume and a molarity, so you know you can easily get the moles right off the bat. Molarity times volume is mixed with 0.2 liters of 0.2 molar, again, of sodium hydroxide in a coffee cup calorimeter. The temperature of the mixture increases 22.15 to 23.18, so you know your delta T. If the densities of the two solutions are 1 gram per mil, the reason you need to know the densities is because you've got a volume, right? You're going to need it in mass, right? What is the value of delta H for the reaction? And that's just your basic neutralization reaction. Acid plus base gives us a salt and water. Okay, so we have Q. Here's our C, right? That's the mass of the material. So we've got 200 milliliters, right? Plus 200 milliliters equals 400 milliliters. 400 milliliters times, that's why we're given the density, 1 gram per milliliter. I've got 400 grams. That's my M. That's my delta T. And we're just using water, even though you've got HCl in there and sodium hydroxide, the solvent is water. The C doesn't change much. You don't have to worry about that. You just use the C for water. So that's the same one we've been using all along. So that's the same. The only catch is you want it per 1 mole because it's for this reaction. So you want it per 1 mole. Okay. So we have this value here, and then here's where we got the, what I did up here, what I said before. That gives me my moles. So now we got a per mole of reactant. Now, if these two were different, the HCl and sodium hydroxide, the question would have to ask you like per mole of HCl or per mole of sodium hydroxide. Or if we had something like a 2-to-1 acid, like a sulfuric acid and sodium hydroxide, then it wouldn't be all one coefficient. You'd have twos. So just pay attention to what it's asking. But this one, clearly, they're the same. It's the way of keeping it simple. So it's basically the same approach. Q equals MC delta T, just doing one more step where we get it per mole. Your enthalpy values are always typically in per mole when you're dealing with chemical reactions. Questions? This is exercise 10.6. Okay, so an actual bomb calorimeter, this is something a little bit fancier than a coffee cup. And in this case, before you use it, you're going to have to know what the kind of like the heat capacity of the whole calorimeter is. Because you've got water, you've got steel, right? You've got the walls, thermal insulated walls, and all this. So all these are different materials. They all have different heat capacities. So the first time you use this thing, you have to determine what its heat capacity is. Because the idea here is what you're going to do is you're going to put a sample here. This is how we can do like foods and stuff like this. Put a sample here. Let's say it's a Snickers bar. We got these wires here. We want to know how many calories are in a Snickers bar. Wires to ignite it. We're basically going to combust it. That's a food material, so we can combust it, right? Basically going to combust it, see how many calories are in there. We can convert joules and calories back and forth, no problem. Okay, so it's all the heat's going to be lost is going to be gained by the calorimeter, right? But it's not just water. We can't use the heat capacity of water because you've got the steel, you've got the tray that it's sitting in, right? You got this container, you got these walls. So you can't do it until you know what the heat capacity of that whole system is. So what you do is you start with something you know. And I think that's what we do here. Solving for the C of the calorimeter. So we take a known substance the first time you use it, where we know the heat associated with, and here it is here. Combustion of benzoic acid releases that many joules per gram. Okay, so now we know exactly how much heat's released by this amount of benzoic acid. We can effectively do something very similar to this right here. Right? Solving it twice. We know how much heat should be released by the benzoic acid, and therefore we can kind of back calculate what that is. So that's what this is here. That's the heat capacity of the calorimeter right there with the capital C. Heat capacity of the calorimeter. And there's something I wanted to show you here because it wasn't clear and I can't remember what it is. Oh, I know what it was because it's 1 gram. So we know there's 26.38 kilojoule, whoops, not kilograms, kilojoules. This is what we're told. 26.38 kilojoules per 1 gram, right? Times, we used 1 gram. Gets me this. If we didn't use 1 gram, so that's why I want to show this step. This doesn't show it here because you don't always use exactly 1 gram. So you're going to have to multiply by your mass to get to your kilojoules. In this case, and then maybe I cut it out, or if it's not shown in the book, let's see, 10.7. Probably different. Because when they do these problems, they have like 6 slides for each problem. 10.7. You know, see, it doesn't really show it. Maybe they say it in words. This is on page 470. So it's important that you realize you have to multiply by the mass. And that's where the 26.38. And then there's my temperature change. Because what I'm solving for is this. That's the heat capacity of this thing right here. The capital C of the calorimeter. That's what that means. Right? I'm solving for that. This is the heat given off by the benzoic acid divided by the temperature change, which we know. Gives me now this. Now I can use that value anytime I want to use this system here. I know the heat capacity of the calorimeter, so therefore I can figure out how many calories were in that piece of food, or how many kilojoules of energy in that piece of food or fuel. So it's simply kind of doing these Q equations twice, just like with the metal, only this time you're doing it once just to figure out the calorimeter, and then you can apply that to any material you put in the calorimeter. So in this case, we have it already, so this is a different one. It's not the same, right? No, this one's 3.6. So it's a different calorimeter. That's the heat capacity of my calorimeter that's given to me. Now we've got a bomb calorimeter. We know its heat capacity. Now, 1.14 grams of octane reacts with excess oxygen in constant volume calorimeter. The temperature of the calorimeter increases by 10 degrees C. The heat capacity of the calorimeter is given. Determine the energy released for 1 gram of octane. And then all you do is Q cal equals C cal delta T. You've got the C cal, that's the calorimeter. You've got the delta T, 10 degrees. That's the 69.7 kilojoules. But it's asking for 1 gram. And you burned 1.14 grams. So you're not done, right? That number there is the heat associated with 1.14 grams. So just set up a ratio and solve it, right? Kind of like 6.9, whoops, not 6.977, 69. 69.7 kilojoules for every 1.14 grams equals, that's what I just did here, but X over how many kilojoules per 1 gram. That's all. Or you just multiply it by dimensional analysis. 69.7 kilojoules per 1.14 gram. Times 1 gram, yeah. Same thing. It's just, it's dimensional analysis, but it's kind of like setting up a ratio. Lots of times that's something you've done before you ever came to this class, thinking about a ratio like that. So thinking about it like this is nice. Hey, if I know this much heat is released for this many grams, how much heat is released for this many grams? That's all. And what do we get? 61.1 kilojoules. So that's the energy released for 1 gram of octane. Questions? Can you tell us what my favorite lecture is here? Hess's law I can handle. I like Hess's law. I don't know. I just struggle teaching this stuff for some reason. That particular material. Hess's law is good. I think we can handle this no problem. This stuff is just, it's a little bit, I don't know. It's not like the math is hard. It's just conceptually tough to kind of figure out which equation to use where, even though they're all kind of the same. You got like 3 or 4 different versions of the same type of equation, and then maybe that's what confuses students. I don't know. I can't figure it out. I can't figure out a good way to deliver it. So, all right. So my apologies. Hess's law. For some reactions, delta H of a reaction cannot be determined directly. And this is the case lots of times. Just too difficult to measure. The energy change is too small to measure. We just can't, get the reaction to behave in the conditions that are easily measurable, whatever. So this is what I kind of mentioned in the video at the very beginning of this chapter, that sometimes we can simply use like puzzle pieces of different reactions. So for instance, have anything else on here? No, okay. So, and I think I might have done something like this on the video. I'm interested in the energy of A going to B, but I can't determine that, right? But I do know how much energy there is in going from A to C. And I also know, and you could think of these as like energy profiles here. And I know how much energy goes from C to A. So you can see that's the whole idea of a state function. The path doesn't matter. The difference between this energy here on the y-axis and this energy here on the y-axis, that's what I'm after, right? So if I know the energy associated with this, right, I can measure this, and then this, you can get the idea. I can take this minus that and solve it. That's the whole point of that's the whole like value of it being a state function, being able to do something like this. So now this can't be measured, but I can still get to that value. All right. So if you look at this particular one right here, this is 2 reactions up top. And if I sum those 2 reactions, I get the reaction down below. So if you notice, carbon monoxide is a product of the first reaction, just like math. If it's on one side of the equation, the other side of the equation, you can eliminate it. So carbon monoxide is a product and a reactant, so I can cancel it out. Because that means, it's a reactant and that's a product, so it's not going to wind up in the overall reaction if I add these 2. So I'm basically adding the first 2 reactions. I get rid of the 3 hydrogens on both sides. Look what I get. I get reaction 3. These 2 lead to this. There's the methane coming down. there's one water there and one water there, right? So I get two waters. There's my 4 hydrogen coming down, and there's my CO2. So if I know the enthalpy values for 1 and 2, I now know the enthalpy value for 3. You can just add them up. That's the whole idea of a state function. Not worrying about the path. All we know is that, hey, methane plus water giving me hydrogen and oxygen has this enthalpy value because these two, right, lead to the same thing ultimately through a different pathway. So the energy change is the same. So when you're using Hess's law, you might have to manipulate the reactions. Here we didn't have to manipulate anything, we just had to add them. In some cases, you might have to reverse them, multiply them by something to get to that final reaction that you want. Okay, so if you reverse the reaction, well, make sure you reverse the enthalpy sign, right? That's all. If I reverse that reaction, change the sign. Obviously, if the top reaction is endothermic, the bottom reaction is exothermic. You're just switching the sign. If I multiply by some sort of factor, make sure you also multiply. In this case, we multiplied the second reaction, not the first one, by 3. So we wind up with a negative still 540. But so whatever you do in manipulating a reaction, make sure you remember to change the sign. Other than that, that's all it is. It's like a puzzle. So we're looking at an example now, and we'll say, okay, what do we need to do here? Use the following data. Calculate the heat of the reaction for the following reaction. We're going to take these 3 reactions here and figure out what the enthalpy for this reaction is. Now, when you first look at that, like Megan, she looks shocked. And you think to yourself, how the heck am I going to, rearrange these and manipulate this? I'll give you a very simple way to do this. Do not focus on everything. Focus on one thing at a time. And also pick things that only occur in one place. So for instance, C2H4, I'm going to start with that. It only occurs on the reactant side, and it also only occurs in this reaction here, and that's it. Now, I know my final reaction has to have C2H4 on the reactant side, and I know I have to have 1 mole of it. So that means I don't have to do anything to that reaction because I have C2H4 on the reactant side as 1 mole, right? That only works because C2H4 doesn't occur anywhere else. When you get to things like water, right? Oxygen it gets a little bit tougher, but once you do these first, things usually fall into place and it's not too bad. The next thing I'm going to do is look at C2H6. And I'm going to say, okay, I need it on the product side and it's on the reactant side. And I need 1 mole. So all I have to do is flip that, right? Flip that whole reaction. So I'm going to do it like this and say times a -1. That'll remind me to flip the reaction and also remind me to change the sign of that enthalpy. And then the hydrogen. Hydrogen's 1 mole on the reactant side, so this one's probably good too. So let me flip this one, and I'll get 2 CO2 plus 3 waters gives me C2H6 plus 7/2 O2. And now I've got 1560. And I put an X through this one to know that I'm not adding that up anymore. And let's add these 3 up and see what we get. Okay. So obviously the C2H4 is only 1 place. I'm going to bring that down here. Okay. Now, we only got hydrogen in 1 place. That's good. H2. So we've got what? 3.5. Oh, wait, I'm looking at the wrong one. Sorry. Oxygen's been flipped. Okay, so that's good. So we've got 3 waters here, but then we've also got 2 and 1 here. So I'm going to cancel out all the waters then, right? 3 on the reactant side, 3 on the product side. I cancel those out. And I've got CO2 over here, 2 of them. I'm going to cancel those out there, right? And then, of course, I've got C2H6 over here from right here coming down. And I'm supposed to have 7/2 oxygen or 3.5 oxygen. Now, I've got, oh, no, I'm sorry, I'm supposed to have 0 oxygen. So I've got, here I've got 3.5. Here I've got 3.5 right there, right? And 7/2 is 3.5. So I keep looking at this one reaction again. That's why I hate 3.5 there. Cancel that out with this 7/2 is 3.5. Bring that down. Done. Now add up these, eliminating this. Don't use that one. And that's our answer. So 1560, negative 285.8, negative 1411. What do we get? What is it?
Negative 136.8.
And that's kilojoules. And that's Hess's law. This is like a puzzle. Look at what you have, manipulate, change to get to the reaction you need. Questions? Here's one here. Oh, this is the one we just did. I forgot I had this whole page here now. All right, so standard enthalpy of a reaction is just standard conditions. That's all it is. Nothing new to learn other than the fact that it just means standard conditions. And for enthalpies, it's 1 bar. That's pretty close to 1 atmosphere. It's not exactly. Any solutions would be 1 molar, and the temperatures are 25 degrees C. The standard state of a substance is the most stable state, physical state. So for oxygen, it would be O2. Okay. Now, standard enthalpy of formation is the enthalpy change that takes place at a constant pressure when 1 mole of a substance is formed from its constituent elements. This is what the tabulated formulation enthalpies will be when you see them. They'll always be 1 mole, and they'll always be from their elements. So the enthalpy of formation, this is an enthalpy of formation reaction. This is not an enthalpy of formation reaction because this is forming 2 moles. Enthalpy of formations are always for 1 mole. Okay, even though this has to meet both those criteria to be a formation reaction, it has to be forming 1 mole and from its elements, which means if I have an enthalpy, I got to come up reaction in my head, but if on the reactant side I have ammonia plus oxygen or something giving me, NO, it's not going to give me NO. You get the idea. This can't be a formation reaction because that's not elemental nitrogen. It always has to be the elements. So O2 for oxygen. Carbon is graphite. Hydrogen gas. These are elements forming. So if you're interested in the enthalpy formation for methane, it will be carbon solid, graphite, plus hydrogen gas, right? As long as you're forming 1 mole, that's all you care about. So it'll be 2 hydrogen gas. That will be an enthalpy formation because you're forming 1 mole. So when you see these are standard enthalpies of formation of selected substances. Obviously, anything that's an element already will have values of 0, right? Lots of times they're even omitted from the tables. This table, they're showing it to you, but lots of times they're omitted because everybody knows they're 0. But then you're looking at, so these are values of formation. The energy associated with forming that substance from its element constituents. And as a result, you can use those with this equation to solve the enthalpies. Another way to get the enthalpy of a reaction. There's Hess's law, where you can manipulate reactions, or there's formation reactions. And what you're doing is simply looking up the value and using this equation and using the stoichiometric coefficients. That's what the ends are for. So what we would do is we take the products minus the reactants. So we take 2 times water. So it'd be 2 times water. What state is it in? Check the state. Liquid. Liquid water, negative 285.8. They're all in kilojoules, these tables. Negative 285.8, that's H2O. Plus the carbon dioxide. What's carbon dioxide? Negative 393.5. Minus the reactants. Methane. CH4 gas, negative 74.8. Plus 0 for oxygen, right? And that's the enthalpy for this reaction using formations. Effectively, what it's doing, that negative sign is effectively flipping those, right? That's what the negative sign does. Because we're not forming methane, right? Methane's a reactant. So it's almost like using Hess's law. It's the same thing. That sign is flipping it because it's not a formation reaction. So you've got to change the sign. You're actually breaking it down, right? You're breaking down methane. So the sign needs to be opposite. This is what this equation does for you. We'll use this equation again in Gen Chem 2 for delta G's and delta S's. It's always simple to remember. Products minus reactants. Just sum them up and remember your coefficients. And that's just another way you can get to the enthalpy of a reaction. If you've got formation table and you don't have, other reactions like these, like we did here for Hess's law, you can do formation reactions. And when you get a problem like this, you can either use Hess's law and flip these, or you can use that equation, right? This is what we just did. But this was there to remind me that you can do this either way. And I encourage you to do it. Now do it like flipping these around. And you realize you're doing the same thing that we just did here. Because the ones that are not forming are going to be the reactants, and the negative sign takes care of flipping it for you effectively. That's all you're doing. And you get the same answer both ways. So calculate this out here, and then do this, not now, do this at home, using Hess's law, just flipping these, doing what you need to do, and you'll get the same answer for both. So that's the end of the chapter. Heating curves and the heat capacity, specific heat capacity with the calorimetry. Heats a reaction, Hess's law, and heats a formation.